Thank you for the invitation to speak. And I'm happy to be here and be in person. So I wanted to start with just a sort of very general thing. So here is sort of like an SAT question. Here are three formulas, one of which is a bit different from the other two. And the first two formulas, I'm sure everyone recognizes. The third formula is the quantum extremal surface formula. And it's a bit different from the other two formulas in some obvious ways. One is, although I haven't put it here, there's an H bar in the denominator. So it involves quantum mechanics and gravity. But there's another sense in which it will lead to a different consequence than the other two. It's sort of philosophically a little bit different. And that is that we're usually taught that both of these formulas on the first two lines are interpreted as senses in which gravity is universal, right? The m cancels on both sides of the first equation, and so that gives one sense in which gravity is a universal force, right? And similarly, the metric only couples to the stress tensor in Einstein gravity. And so the question is, in quantum gravity, is there a sense in which gravity is universal? And if so, exactly how is it universal, and to what extent is universality modified compared to in classical gravity? Okay, so that's a very vague comment, but I'm going to try to convince you that what I'm talking about is at least somewhat in this direction. Okay. So first, let me give you some evidence that quantum gravity is not exactly that universal in the black hole interior, and this is mostly previous work. So first of all, we care about the black hole interior because it's the place where both quantum mechanics and gravity are strong in some sense. And there are various qualitative arguments that suggest that the interior of the black hole, at least for very special cases, not astrophysical black holes, but some very isolated black holes, are non-universal. And I think one of the oldest and most popular one is the firewall argument by Amps, right? It suggests that there's something very special happening at the horizon of the black hole, of a very old black hole. More quantitatively, various people, particularly Schenker and Stanford, have shown that the energy levels of a black hole obey universal random matrix statistics. So that sounds a bit like universality in the sense that no matter what black hole you consider, whether it's supersymmetric, non-supersymmetric, charged, not charged, no matter what the details of the theory, we expect that the energy levels of the black hole to obey some sort of universality. However, it's believed that the detailed spectrum of the particular black hole that you're interested in is highly theory dependent, in the sense that you just change any one of the coupling constants of your theory by a tiny little bit, and the energy spectrum will be totally different. The precise energy levels. So it's not like the hydrogen atom, for example, where if you turn on a small perturbation, the energy levels will only change a little bit. Here we expect something more dramatic to happen. Okay, but the reason why I gave these two, the first argument has the advantage that it's qualitative, but it involves the interior. So the disadvantage is that it's qualitative, and the second argument has the advantage that it's quantitative. It's about some calculable thing in principle, the spectrum of the black hole, but it's not obviously about the interior of the black hole. Okay, so the idea of this talk is to try to give an argument that's both a little quantitative and it also directly involves the interior. Okay, one more slide of intro. So this is just an example of some calculation that people did in some toy model of a black hole. And it's the spectral form factor, as many of you probably have seen. But the important thing is this red jagged line, which is evidence that the spectrum of the black hole is very complicated. And if you change the theory by a little bit, by changing the couplings, this red jagged line completely changes. And similarly, you can look at matrix elements of certain operators in some toy models of black holes, and you see that they look very chaotic. I mean, chaotic here, not in a precise sense, but in a somewhat pseudo-random fashion. Okay, so the idea of this project is to use the quantum extremal surface formula to make this problem more precise. So what we're going to do is we're going to ask whether the black hole interior can be reconstructed in a quantum information theoretic sense with limited knowledge of the couplings in a holographic theory of gravity. So you could imagine that you have, whatever favorite model of particle physics that you like, and you don't know the precise value of the couplings, but you imagine that this particle physics model is embedded in some model of gravity that is holographic. I'm not going to say explicitly what the boundary dual of that theory is, but I'm just imagining that that theory is holographic, and that changing the couplings of the holographic theory corresponds to changing some parameters in your boundary theory. I'm not going to be very explicit. In some cases, I'll be more explicit. In some other cases, I'll be somewhat implicit exactly how those parameters are mapped. And another point worth emphasizing is that the inability to do bulk reconstruction in the black hole interior, which we're going to discuss, will be a non-perturbative effect in 1 over g Newton. So it's in some sense a very quantum effect. All right, here's the outline for the rest of the talk. So I'm going to define the setup, and then I'm going to discuss a computation of the entanglement wedge in gravity, and that's going to be a rather technical part of the talk. Then I'm going to discuss replica wormholes in a simpler model of gravity known as JT gravity, and the SYK model. And I will make some conclusions which suggest that our findings are much more general than the particular cases that we consider. Okay, along the way, we will have some connection to the factorization problem, chaos, the Schmidt Echo, etc. Okay, but let me start by defining the setup a bit more precisely. So imagine that, as I said, we have a holographic system which is dual to some theory of gravity, and it has some couplings, J. So J you can either think of as the boundary couplings, or by holography, they're related to some perhaps couplings in the bulk or some boundary conditions of fields in the bulk. Okay, so we're going to consider a state of the system which is the thermal field double. That's the beta plus ITJ. Okay, that's the thermal field double. It's just e to the minus beta h times the sort of identity state. We're going to entangle the thermal field double with an auxiliary system which we call the journal. So we have now the original holographic theory, and we've invented some new auxiliary Hilbert space, which just records the value of the couplings. We call that the journal. So it could literally be, for example, a free particle just sitting on a line, and its position records the particular value of the couplings that we chose to make the thermal field double with. Okay, and we sum over the possible values of the coupling J with some particular weight. So in this formula, I'm only assuming there's one coupling. In other formulas, we'll have many couplings, but it's basically the same formula. Okay, so this is a particular entangled state between a theory, a holographic theory, and some reference system. And the holographic theory, at some appropriate values of temperature and perhaps chemical potentials or something, will correspond to a black hole. So we're going to say that this is a state of a black hole entangled with a journal.
Sorry, but why can you do that? Because J are the couplings of the theory. So yes. You have a theory with an electric charge, a theory with another electric charge, etc. And I mean, there is no reason why you could write a Hilbert space for different electric charges would make sense. There is no, I mean, why should I am allowed to sum to linear combinations of vectors?
Yeah, that's a good question. That's a good question. So, well, in the cases that we're going to be considering, we're going to have a quantum mechanical theory, in which case that the issue of changing the coupling. So the question is, in quantum field theory in general, if you change the couplings, you have a totally different Hilbert space. So what does this mean in the formula? First, let me just sidestep the question by saying, let's consider quantum mechanics, where there are particular examples of one-dimensional quantum systems which are dual to two-dimensional black holes, in which case the couplings can be just changed, just like a harmonic oscillator. You can change the couplings, and different states of the harmonic oscillator with different couplings are still in the same Hilbert space.
Well, they are in the same Hilbert space because actually all Hilbert spaces, even in quantum field theory, are isomorphic, not canonically, but they're isomorphic. But what you cannot do, even in quantum mechanics, is to take, say, a harmonic oscillator and then accord the potential for a theory with 1 degree of freedom, and then sum the Hilbert spaces of the two.
Yes, so we've attached, so for the case of the harmonic oscillator, right, let me be more explicit. So this beta plus I, let's call the state beta of the harmonic oscillator, right? And then we're tensoring with some auxiliary system that's, let's say, a free particle. And the free particle has some position x. and the x just records the value of j, right? So this beta, for example, to take an even simpler example, it could just be the ground state of the harmonic oscillator with some quartic interaction j, right? And then I'm allowed to write down this formula.
Again, that I don't understand, because if j was a quantum variable, right, then you can entangle, for instance, with the detector and then write that object. But you are assuming that this j is a quantum variable, it's not a number.
Yeah, I'm promoting it to a quantum variable. Yeah. So, for example, this thing here is just some wave function. It's some Gaussian wave function. Let's say, let's take j to be the mass of the harmonic oscillator, the frequency of the harmonic oscillator, right? It's just some wave function, right? Let's say it's this, right? With sigma is now related to the frequency, right? And this is the wave function for the harmonic oscillator. Now I just tensor the theory, let's say with another, this could be another particle that's just totally non-interacting with this theory, right? And I say that the wave function is delta of sigma for this particle.
Okay, so you are promoting sigma to a quantum variable.
Yes, so I'm promoting the couplings of the theory to a quantum variable, and there's some auxiliary device which records those quantum variables.
And does it make sense, again, because I mean, when you promote a variable to an observable to a quantum variable, then for me it makes sense if then that's a quantum variable, namely there is a Hilbert space, and in Hilbert space you have two vectors, you can sum them, you can multiply them by phase, etc. But that's exactly what we don't see in a harmonic oscillator, right? I mean, unless this harmonic oscillator is part of a bigger system. If I have a spring with a given k, that's it. K doesn't obey any uncertainty principle.
Yes,
it's not true that if I measure k with arbitrary precision, there is some dual variable that become all spread over. And I have never seen a single spring which is in a superposition of two different elastic constants.
Yes,
superposition,
yes.
Right?
Yes.
Where you can take, like, you have, say, the two-slit experiment with k. So you are making a very big assumption here.
Yes, this is.
I don't see how it's justified in any sense.
Well, we're not making an assumption exactly. We're just creating a setup in which we can do this.
Yes, but my point is that since this setup, in this setup, you should also be able to do a double-slit experiment with the coupling constants.
Well,
otherwise they are not.
I don't know how to experimentally. I agree that I don't know exactly how to experimentally realize this setup, but I think there's no problem with mathematically considering, two particles and interpreting one of the positions of the particles as entering the Lagrange. I mean, perhaps this is too simple, but you could start with a theory with two particles, right? And then there's some coupling, let's say, between the two particles, and you could interpret one of them if one of the particles is very heavy, let's say, right? You could interpret its position as giving some coupling constant to the other theory, right? So that's kind of the philosophy that we're going. So you can imagine that this journal is some very heavy degree of freedom, which is almost classical, that we normally it's just fixed, but for some reason, if you could really access it by exciting it in some way, But in the particular cases which we're going to discuss, this is just a mathematical tool so that we can ask a quantum information theory question. I'm not claiming that in the actual universe there's a journal system somewhere.
So because you could say the universe is one fixed j. J is not a quantum variable. It doesn't have a conjugate variable. J does not obey an uncertainty principle. They can't superimpose it.
That's right. But for example, in many holographic theories that we know, in all holographic theories that we know about, there are couplings of the theory, and it makes sense to formally consider this object, whether or not. I mean, you might say n equals 4 super Yang-Mills may or may not be realizable in the lab. But suppose I realize that there's some marginal parameter, right, which corresponds to the n equals 4 super Yang-Mills, and I'm allowed to, in my mind, imagine that in however way I prepared the lab system, that variable is controllable by some very clever experimentalist, and then they can prepare some system which records the particular choice.
Yes. No. What I don't understand is why that particular variable is quantum. Yes, I can control a coupling constants, but I don't understand why it's quantum. I mean, again, the coupling constant of super Yang-Mills, G Yang-Mills, is not you can say you have to change the theory to make it quantum.
Yes, I'm changing the theory if you like. Yeah, I'm just enriching the theory in such a way that I'm allowed to consider this superposition. But yeah, it's not. I agree, it's not part of the usual way of thinking about coupling constants.
I mean, it's really a different theory.
Yes, it's a different theory. It's a different theory. The Hilbert space is now different in particular, right? It's enriched by this additional degree of freedom. It's now the Hilbert space is a tensor product of the original theory and this auxiliary system.
And by the way, in this new theory, there will also be some coupling constants. So do you also entangle them with a journal of a journal?
No, we don't do that. But yeah.
Because I mean, I think that you are opening the
But
Pandora's box.
it's
Anyway.
different, like add an axiom to QCD, right? So you can consider QCD or you can consider QCD with an axiom. I think that would be.
Yeah, but QCD with an axiom also has some coupling constants. And and those are coupling constants that you don't superimpose them.
But then you
anyway,
could
so-
regard the thetas as different expectation values of the axiom field, for example, right?
Yeah.
Likewise, the J's could be set by
Yes,
that.
then in that case, I would say, no, the axiom is not a coupling constant, it's a field.
Right.
But then there is a coupling constant, there is lambda QCD, for instance, and in that theory is fixed. So again, for me, I need an operational meaning for like doing something.
But is it important for you to do that for all coupling constants?
No.
So in that sense,
yeah.
well, you do it for some of them. And
Yeah, it's a choice. It's a choice for me what your setup. I mean, maybe it would help to think about J as a super selection sector. Does that help? Right. If you have a super selection sector in your theory, you could imagine having some device which is entangled with the particular super selection sector. I mean, just formally, that's some state that you could write down.
I mean, again, I think that one ends up by doing something that is not the original theory, but let's go on.
Okay. Okay, so if we consider this particular state, just to introduce something which we'll come back later to, for example, the Hamiltonian could be the SYK model, which has all these coupling constants J. And the J here would refer to the n to the q variables, Ji, Jkl, right? Sometimes I will slip up and call the SYK model the quantum dot. But you can imagine entangling the SYK model where you take many of these thermal field doubles with different values of J, entangling them with some J. And so now this journal Hilbert space would be the Hilbert space of n to the q particles, one for each couple. The question we're going to ask is, when we consider this entangled state, we then apply some unitary u to the, let's say, the quantum dot, right? And we evolve the system by a long time t with the usual Hamiltonian time evolution, right? Then we want to ask, can we recover information encoded by u without access to the journal part of the Hilbert space, right? So we trace out the journal and we ask whether or not the information that we threw into the black hole, which is the unitary u, right, can be recovered just by looking at the system or not. Just to draw a little diagram to make sure this is completely clear, right? So we have these are some qubits that represent the SYK dot, right? We created some entangled state. That's this entangled state here that I guess we call psi. So this is some state psi, which is entangled with some journal, right? So there's also some journal Hilbert space. Maybe I need to color. Right? And we applied some unitary u on maybe a subset of the qubits of the SYK system. It encodes some information that we throw into the black hole, and then we just apply the usual e to the I ht, right? The e to the I ht operator though depends on both j and it acts on the SYK system. So we can think of it as sort of like a controlled operation.
And the U is the same for every J?
The U could be, yeah, it could be the same for every J. That's right. For different choices. So J now is just some auxiliary variable, which is indicated by this yellow line, and these are some qubits. Right? So this is some free particle, and these are some qubits. We apply U. Maybe U could be chosen from a set of possible U's. So like you could throw in a journal, you could throw in various different objects into the black hole. That corresponds to changing U. But then we evolve with the same Hamiltonian, which is just this coupled Hamiltonian, right? H is just this thing, where J now is a quantized operator, right? It's an operator that acts on the journal Hilbert space.
And U is made of size,
Yeah, U is made of size.
only
That's
of size.
Only of size, that's correct.
And it acts on one of the two in the thermal field, or
We considered several possible cases.
And there is no separate dynamics for J's, right?
No, the overall Hamiltonian is just this. So J is now, you could put a hat here if you wanted to.
So what do you mean under recovering information about this? Like recover you completely, like polynomial in psi?
Well, we'll make that a little bit more precise. I mean, what I mean is, for example, you can compute the relative entropy of this system when you trace out the German,
Yeah.
and you want to ask whether the relative entropy is large when you choose different U's.
Yeah, but it's not enough information, sometimes like one bit of information.
Yeah, so this is a probe question, yeah. So you here, I'm imagining, is just a probe, so it only acts on a few, maybe 3, 4, 5 Majoranas. And there's a large N limit.
And if I have an access to the journal, I can restore you.
Yeah, if you had access to both systems, of course you could restore the you could figure out what information I threw in because it's just unitary time evolution. But the subtlety here is I'm tracing out U, so I'm saying.
That's why it's not unitary. Because if you trace out.
Yes. So it's a non-trivial question now whether you can recover information just from a subsystem.
And it's not trivial even without assuming that it's thermal field double, right? So
That's
far
right.
it wasn't.
That's right. The thermal field double is only just for simplicity for the graphic calculation. Okay, so let me just define the entanglement wedge very quickly. So the entanglement wedge of a subsystem rho is a region of spacetime where a probe qubit can be reconstructed. So it's probe because I'm not imagining that it's scaling with n or anything like that. For a black hole in thermal equilibrium, the entanglement wedge is just bounded by the horizon, right? So this is in thermal equilibrium, you just say that the exterior of the black hole is in the entanglement wedge of the quantum dot, and then what's behind the horizon, you don't know. The spatial complement of the entanglement wedge is the entanglement wedge of the purifying system, right? So in the thermal field double, the spatial complement would be the other side of the black hole, right? And you say that that's the entanglement wedge of the other side of the thermal field double, right? And similarly, if you have a more complicated setup like this, you would still say that whatever the entanglement wedge of some subsystem, the complement of that entanglement wedge is the entanglement wedge of the complement of the boundary system.
Okay, but this U, for you, does it act only on one side of thermal field double, or it acts on
Yeah, so let's take for simplicity that it only acts on one side of the thermal field double, but that's not crucial. Okay, so this is just a spoiler, but basically what we will show is that at late times, the entanglement wedge of the two quantum dots, it looks like this. There's two exterior regions where the entanglement wedge contains these blue rectangles, but then there's some region that's missing. And so if you had a probe qubit that fell in at an earlier time, you would not be able to detect whether or not that probe qubit was in the upstage or the downstage or anything like that. All right, so how do we compute what the actual regions are, those blue regions that I was discussing? We do so by using the quantum extremal surface formula. So this was discussed by many people. Actually, it probably goes all the way back to Bekenstein and Hawking. This is just some big generalization of Bekenstein and Hawking. And it says that what you do is you compute the so-called generalized entropy. The generalized entropy is the area over 4g Newton plus the matter entropy. This is usually a small correction, but it's there in principle. And you compute this generalized entropy, and then you extremize over the choice of location Q. You extremize over the choice of that region, the blue region. So you consider many different blue rectangles in the previous slide, and you find the one which is extremal, according to this formula. And the one which extremizes the generalized entropy is the one which actually corresponds to the real entanglement wedge of the system. Okay, and if there are multiple extremum, you take the minimum one. That's one little subtlety that I did not break down.
And I was, sorry, what was the
Yeah, so the idea is that a slight improvement to the entanglement wedge formula is that you should also include islands, which I denote by I. Yeah, so in this previous case, for example, if you're computing the entanglement wedge of the complement, you're allowed to consider islands, which could be some region in here, could be some region in principle, could be anywhere, but it's some disconnected region from anything else, and you also extremize over the position of the island. Okay, so now we're going to discuss the computation of the matter entanglement entropy in a holographic theory of the kind that I was discussing. And just a warning, this is a little bit technical, so if you fall asleep at some point, I'll alert you when to wake up and pay attention to it. Okay, so in order to compute the matter entanglement entropy, so first of all, in that previous formula, it had an area term, which is trivial to compute, and then there's a matter entropy term. The matter entropy term is the most difficult thing to compute. So I'm just going to focus on that now. In order to compute that, we're going to first compute trace rho to the n, and then take the n goes to 1 limit to extract the usual entropy. Remind you that this is not a boundary calculation right now. We're still doing the quantum extremal surface. So this is a bulk calculation of trace rho to the n. Okay, so we're going to do this computation in the bulk, which means we're going to look at the matter entropy, the entropy of quantum fields with certain funny boundary conditions and potentially with twist operators. Okay, and there's going to be two parts. One candidate surface is just the empty set. So here I've shown the entanglement wedge, the candidate entanglement wedge of the system or the quantum dot, and the candidate entanglement wedge of the complement, which is the entanglement wedge of the journal. Right. This is the complement. Everything is a complement of the empty set, and the exterior is a complement of the interior. So, all right. Now let's discuss this computation in a little bit of detail. So, for simplicity, we're going to consider a model which is JT gravity. It's some two-dimensional theory of gravity that arises in some special limit of Einstein gravity. And we're going to consider a special matter theory, which is just a conformal field theory in the bulk. And we're going to choose it to be conformal for technical reasons. More so, we're going to choose the conformal theory to, it's going to be enriched with a possible choice of boundary conditions B, right? So it's a BCFT. And the boundary conditions are labeled by J. So the simplest case is just the case of a compact or non-compact boson, where we have some possible choices of Dirichlet conditions in the bulk. And the choice of Dirichlet boundary condition is labeled by J. So J labels the position of this scalar field. Right? This model is actually a bit sick because it has a global symmetry in the bulk. And I can discuss this more later if anyone wants to discuss it. But nevertheless, even though it's a little bit sick, it seems to be a pretty well-defined effective theory.
How does the JT gravity couple to this BCFT?
Yeah, we assume that's minimally coupled. So at the end of the day, what we're interested in is the Renyi entropy, trace rho to the n. Now let's think about what that actually means. Trace rho to the n is, for example, we can think of it as the matter entropy of the journal, right? So this involves summing over many matrix elements, rho ij, rho jk, rho ki, let's say for n equals 3, right? And these indices now, because of the setup that we're interested in, correspond to different choices of boundary conditions, right? I and j now correspond to various different elements of the journal Hilbert space, which are actually different couplings. So what we're actually interested in is computing, if we're interested in computing something like rho ij in order to compute this trace rho to the n, we will have to consider a geometry where one of the top part of the geometry has one boundary condition, which is green, and the bottom part has a different boundary condition, red. And then we're going to consider, let's say, 3 copies of this to compute trace rho cubed, and then sum over all those indices.
So why the trace doesn't have any psi variable? I mean, you have a Hilbert space made of the
Yes,
size, right? But they don't seem to appear in that formula.
Yes, so I'm thinking of this as the Renyi entropy now of the journal thing. Of course, when I actually compute these things, these are just the boundary conditions, and we have to sum over all the quantum fields living in this bulk. Yeah. So this is just some BCFT calculation where you have changing boundary conditions, and then you first compute the BCFT answer for each value of i's, and then you sum over all the i's. Okay, this seems like a silly thing to say, but you could of course quotient this picture, in which case you can think of this as having n CFTs living on one surface, and then you have many possible, now ij runs over not just one boundary condition, but it's the boundary condition of the tensor theory. The reason why I will use this quotient picture will become more clear in the next few slides. So,
Eric, can you say again where do you insert? What do you insert at the black dots? The boundary changing operator.
yes, yeah, that's exactly right. That's the boundary condition changing operator. So let's imagine that one of the green line could be, you set the value of phi to be some constant, and the red line is some different constant.
Yes.
And then there's some boundary condition changing operator that changes the boundary condition from that.
But there are many, so you insert the ground state.
Yeah. I will discuss this in the next slide. But yeah, it's the boundary condition operator that changes you from ji to ji plus 1.
Right. But that's not unique. There is not. I mean, you're talking about the compact boson, real boson with three boundary condition, right?
Yes.
There are different boundary changing operators.
Yes, that's right. So there's the sum over windings that you in principle also have to do. Yeah, let's say I'm choosing the minimal one.
Okay.
Yeah, this is actually a subtlety. Yeah, if it were the Ising model, which we also considered, then it's unique, and we don't have to consider this subtlety.
Well, there's a unique primary, but there's descendants.
Yes, it's the primary one.
Okay.
So, okay, you get some formula like this, and the only point of writing down this formula was to emphasize that the only kind of data that appears from the actual CFT is just the dimensions of these operators. Right? You basically get a bunch of 2-point functions which are completely fixed by conformal symmetry. So for a free boson, you can compute this dimension of the operator very simply. I don't think I will review this too much. Basically, you think of the boundary condition changing operator as that black dot, right? And you think of the scaling dimension as the dimension, the eigenstate of the scaling operator, right? But then you can do a conformal transformation to map that to the strip with 2 different boundary conditions. And then it's just like a standard sort of string theory calculation to compute the mass of a string, basically, which stretches between 2 different d-branes, right? And you get the same formula that, you'll remember this from Polchinski, let's say. Okay, so you get some formula for the dimensions, and you can make up any probability distribution that you want. We chose to make it a Gaussian distribution, let's say for the non-compact boson, and for the compact boson, we considered a uniform distribution. And if you take, so that corresponds to some Gaussian uncertainty in the particular values of the couplings of the boundary theory. And then you do some integral, and then you get some answer. And the subtlety is you get some answer, but it's in terms of z of n is some Gaussian integrals. So you say, oh, that's so easy, I can do a Gaussian integral, and you get some determinant. But you have to analytically continue that determinant in n, to n goes to 1, and that's quite subtle. So I'm not going to go through that, but you actually can do the analytic continuation with the help of a bunch of little tricks. And you get some final answer, which looks like this. So the matter entropy of the entire ADS region, or the matter entropy of the candidate surface, which is just a trivial surface, grows logarithmically with time. Okay. Let me review, just because this was a bit technical, let me review what we were talking about. We're discussing the entanglement entropy of the journal, and we're considering the case where the entanglement wedge of the journal is nothing, right? We're considering that as a candidate possibility. And what we're saying is, if that were the actual surface for all times, the entropy of the journal would grow logarithmically with time. So this is a paradox, because the entropy of the black hole is at most a finite answer, right? It's just S back and Sigma-Hagen. And you can't have something that grows, even though it's a log, it's growing quite slowly, there's still going to be a contradiction at very big time. Okay, so the resolution is going to be that there's a new quantum extremal surface that appears, that saves the day. It's going to be quite similar to the evaporating black hole, but there's no evaporation or anything going on here.
Sorry, can you remind me of what is little m again?
Little m is the standard deviation of the probability distribution of the couplings. So that was an input that you can choose to be whatever you want.
Okay, so it's defining this p, okay.
Yeah, it's defining the p. In the case of a non-compact boson, where you just choose a uniform distribution, then m is just related to the radius of the compact boson. Yeah. Okay, why is there a unitarity paradox? Well, we'll see that this is because there are, in some sense, too many states. So what that means is that we're considering some setup where the semi-classical answer is that when you change the value of the couplings, you get very different states. So like the thermal field double with one value of j is almost orthogonal to the thermal field double with another value of j at late times, right? And that's just because of chaos. It's kind of like saying you evolve the system forward with one choice of j, and if you were to have evolved the system forward with a different value of j, then the states that you get at late time are very orthogonal, right? That's the correct answer semi-classically, but it's impossible that that's the end of the story, because if they're all orthogonal, then you would find an arbitrary number of states, and there's at most S. Beckenstein-Hawking. All right, so now let's go to the island case. The island case computation is more complicated because you have to insert two twist fields. So you insert two twist fields with these funny boundary conditions. So in principle, you have to do a BCFT calculation with two twist fields and two insertions of some operators, boundary operators, right? And that is not fixed by conformal symmetry. So it's quite complicated to do this calculation in full generality. But there is a limit in which we can evaluate this, and that is the limit where the twist field is in some sense very close to the boundary dots, right? In that case, we can do some sort of OPE expansion. And when we do the OPE expansion, basically we just have to consider a two-point function, and that is fixed by conformal symmetry. So in some expansion, which I will be a little bit more precise about later, we can do this computation. So an intermediate step, therefore, is just to first consider the case where you have one twist operator and one boundary condition changing operator. And this is the peninsula calculation. So this would correspond to a geometry like this, right? Where you have, here's your n-fold geometry. You have a branch cut here, right? And at the branch cut, you paste to a different geometry, which has a different value of the boundary condition. Okay. This thing here is a bulk to boundary two-point function, which by the fooling trick is roughly like a three-point function, right? So it is fixed by conformal symmetry, and it involves, though, a little bit more data. It does involve more data than the previous calculation, which only involved the scaling dimensions. Now, in principle, the OPE coefficients will show up and so forth. But you can do the calculation, and for a compact boson, we get some plot like this, which shows the generalized entropy after you've done that. And this is the generalized entropy, so it's the matter entropy plus the dilaton, and you see now that there's some extremum, right? So if there were no matter entropy, the extremum would just be at zero. That'd be the horizon. And now the matter entropy, sorry, ignore what I just said. The important point is that there's an extremum. Yeah. Okay, so physically what we're saying is this OPE limit applies when this dot here is very close to this dot here. Of course, they never can be that close in a Euclidean geometry, but in a Lorentzian case, they can be almost null separated. And when they're almost null separated like this, the distance between these 2 points is quite small, and therefore our justification was, therefore our approximation was justified. And you can see from this picture here, right, that at very late times, if these 2 points are nearly null separated, the calculation will look like a peninsula, right? You don't know the fact that this is an island. It looks like a peninsula. Is that clear? Okay. A very similar thing happens in the evaporating black hole, which is the picture on the left. So there's a very strong analogy to the evaporating black hole, but the calculation is a bit more complicated because of all these boundary condition changing operators. Okay, so to summarize, so now is the point where you should wake up again if you haven't been following all the technical details. The point is that what can we reconstruct without knowledge of the couplings? From the boundary point of view, with just access to this quantum dot, what we're saying is that at early times, the black hole interior and exterior is reconstructible. Basically, everything is reconstructible at early times if you throw in some information. But at late times, due to this unitarity paradox, an island appears. And when the island appears, that is the entanglement wedge of the reference system. And because of the complementarity principle, I mean, the principle of complementary recovery, that means that whatever's in the island cannot be reconstructed from the black hole. So the summary is, if you throw in some information into a black hole and then wait a long time, because of chaos, you won't be able to reconstruct it unless you know the precise values of the couplings of the theory that you used in making the black hole. If you were a little bit uncertain about your particular choices of couplings, then that uncertainty would be magnified by chaos. And eventually you will have no information. Well, there'll be a phase transition at some point where you suddenly won't be able to recover any information about what you threw in. So yeah, just to make this a little bit more practical, imagine that you realize, let's say n equals 4 super Yang mills somehow on a lattice, right? What we're trying to say is if you don't know the precise value of G Yang mills on the lattice, right? For example, you can't tune all of your parameters, or you couldn't even tune, you have some lattice and maybe you're not able to tune away all the irrelevant parameters. You might have some trouble doing these sort of black hole experiments because without knowledge of that, you won't be able to recover information that you throw into the black hole. And similarly, even if you let the black hole evaporate and so forth, we expect a similar conclusion to hold.
So where it was important that this is black hole for the existence of this HEP limit?
Yeah, so the reason why it was important that we had a black hole was in this island calculation, the area term was already extremal by itself at the horizon, right? And the matter entropy term, which is usually quite subleading, because the area is extremal at the horizon, by perturbing it just a little bit, you can find a new solution. That's good. So the value of the dilaton, right, is large here, and then it's extremal here, and then large here, right? And so it was important that the dilaton was almost flat in this region here. Otherwise, we can never get an effect which competes with gravity. I might come back to that in a second. Okay, let's try to do something a little bit more practical. So in the previous model, I said, imagine there's a scalar field and we don't know its boundary conditions, etc. But I can't tell you exactly what the quantum dual of such a theory is. So here we're going to do something very practical, which is we're going to look at the Syk model, which unfortunately we don't really know what the bulk theory is, but we're going to find a very similar phenomena. So, and this is going to be related to the replica wormholes. So for those of you who maybe haven't followed the island story very carefully, when you compute the von Neumann entropy, trace rho log rho, you get this island contribution. If you are computing instead the Renyi entropies, trace rho to the n, what ends up happening is you have these replica wormholes, which are these multi-boundary geometries. And that is a sign that even before taking the n goes to 1 limit, if you find the replica wormholes, that is a sign that in the n goes to 1 limit, you'll have an island. Okay, so that's the kind of logic that we're going to do. We're not going to compute now the von Neumann entropy. We're going to compute the Renyi entropies. We're going to find evidence of a replica wormhole, and we're going to say, okay, that means that probably when we took the n, if we take the n goes to 1 limit, we will have some island. Okay. And the reason why we don't compute the von Neumann entropy is just because it's very difficult to do so. Whereas the Renyi entropies only require you to simulate a couple of copies of that. Okay, so for example, the simplest case is trace rho squared, right? What we're going to do is we're going to look at trace rho squared. The matrix elements of rho, again, are given by, are labeled by different values of j, right? So in the Syk model, we can actually choose j to be all n to the q couplings of the Syk model. And then we're going to compute the Renyi2 entropy numerically, actually, just by actually computing this overlap for find and Syk, right? So that overlap here is just the overlap of two different thermofield doubles with different j's. You can calculate e to the minus beta h, in the computer, and you can just calculate this inner product. Then we average it over j with a particular probability measure, right? Which is just the standard measure that you'd use in Syk. So the idea is that we can just Monte Carlo sample this quantity. The Renyi2 entropy can just be Monte Carlo sampled, okay? Now, that is the actual answer that we should get if we do the calculation properly. But we can consider an approximation, which we call the no wormhole approximation. But no wormhole approximation says instead of averaging at the end, instead of first squaring this quantity and then averaging, first average, then square, right? That would be a computation that you can also do numerically. And our interpretation is that that computation removes all possible wormholes, right? Because then instead of having 2 copies, you only have 1 copy. So it's the contribution that would survive, even if you manually disallowed all possible connections between the replicas. Okay. So the upshot is that this is basically some sort of order parameter that allows you to detect numerically whether or not there is a replica wormhole or there's no replica wormhole, which in turn is sort of a signature of whether there's an island or there's no island. Okay, so there's some chain of reasoning which we hope is correct, and well, we have lots of evidence that's correct. So here's the plots. You see, this is the no wormhole approximation in the dashed lines, and if you look at the trace row squared, it just decreases to very small values. These are very tiny values of trace row squared at late times. And in particular, without doing any further calculation, you know that there's some problem. And the reason is that trace row squared of a finite dimensional Hilbert space is bounded by 1 over d, right? If rho is a mixed density matrix, that is the minimum possible value of trace row squared. And because we're getting an answer that's smaller than this, you know that there's some inconsistency with our approximation. And this is very analogous to what I was discussing previously, where we did some bulk computation and we were finding some contradiction with Unitary. Now we are doing some boundary calculation numerically, but we have an analogous paradox. Of course, since we made the mistake, we know exactly how to fix it, which is simply average at the end and not average before you do the square. And if you do that, you see that, of course, the answer avoids the Unitary problem. And this gap between this correct line and the incorrect line is a wormhole contribution in our interpretation. We actually did more checks that I won't explain. Like we computed correlators and things, which show that the solutions behave as if there was a wormhole in the bulk. But this is the basic test. Okay, another thing that was kind of interesting is you can take the SYK model and pretend like you know all these couplings exactly, okay? But you add to it some operator, which is higher dimension than this operator, right? So normally we'd call that irrelevant at low temperatures, right? If you do so, we find a very similar looking plot. So again, this is the no wormhole approximation, and it looks like it's decaying to very, very small values. And there's a big gap between the actual answer and the no wormhole answer. So it suggests that even in the case where we have some irrelevant operator, the physics is quite similar. And again, the correlators and so forth behave fairly similarly, as far as we can tell. Now, the only reason why I say this is normally what we would call an irrelevant operator is in order to really analyze whether it's relevant or irrelevant, you really need to be in the conformal regime. And numerically, it's just very difficult to access the conformal regime in the SYK model. But we also did some analytic calculations in the large QSYK model, which seem to confirm, well, indirectly seem to suggest the same conclusion. So we're fairly confident that if you were to push the numerics, you would find that there are some wormhole effects, even for an irrelevant operator in the conformal regime. So that is an attempt to justify the statement that if you have a black hole and you just don't know some, the couplings of some very high dimensional operator, if you're willing to wait around for a very long time, this high dimensional operator, because of chaos essentially, will destroy any coherence, and you will not be able to recover the diary that Alice threw into the black hole. Okay. That's a bit, I should also say that the way that that happens is not what you might normally expect, which is just that, well, you don't know the coupling, so the bulk quantum field theory gets messy. Okay, what's actually happening is that there's some sort of non-perturbative effect in gravity, which kills you at the horizon in some sense. And so, although this part of the, this sentence that I'm saying is very speculative, we believe that this is evidence that gravity is not very universal, in the sense that in the interior of the black hole, there's sort of these very non-perturbative effects that are highly dependent on the particular theory. And as further evidence of this, you can look at the matrix elements. let me just let me table that discussion for just another second. Okay, we can also search for the right.
Okay, sorry, I have a question on the previous slide. I'm missing the logic flow. So when you say I cannot reconstruct, or an observer cannot reconstruct K, or yeah, you're talking about K, right? In this case now, not different couplings, J.
No. So
Still J.
K is for known and J is unknown.
Okay, but so let's say I'm an observer made out of little size. So can I not measure K directly then in my theory, or are you assuming it's such a high dimensional operator that I could not possibly measure K?
Yeah, I'm assuming that it's roughly like the second category. Yeah, okay. Roughly speaking, I'm imagining that the effect of J in the bulk is turning on a profile of a scalar field, which is a very high dimensional, let's say a very, very massive scalar field with a mass much bigger than any accessible mass that the particle physicists could access in the bulk. But what I'm saying is that that scalar field, which has an extremely high mass, let's say, still has some important effect in the bulk, which is not just directly related to trying to measure that. And it's the place where the effect becomes important is the interior of the black hole. And in particular, yeah.
And so how would you measure this entanglement entropy in principle? Like how could you tell the difference between between different Ks?
The short answer is I don't know how to measure this directly from the bulk point of view. From the boundary point of view, we just did it with the numerics. You have explicitly the boundary dual of the theory. This is a calculation that's well defined in the boundary, but I'm not giving you a bulk. I'm not giving you a bulk experiment that directly measures this quantity. I mean, roughly speaking, yeah. Well, what you could do is, I mean, the literal interpretation of what I'm saying is you prepare a black hole in many different copies of the black hole, and you somehow change the couplings of the theory for each of the black hole that you're preparing. That sounds very difficult to do, and yeah, I'm not sure.
Terry, is there any understanding of this deformation to the putative ADS2 dual of the Syk?
Yes. So in particular, yeah, if you look at the correlation functions of this operator, it behaves in the conformal limit like some operator with some high dimension. Yeah, with some dimension Q2 over Q, basically. So if you make Q2, 100 times Q, it would be some very irrelevant deformation. And well, I'll make another comment about that later. But normally in the bulk, you don't see any effects of this high dimensional operator, right? As you go into the interior, you see, I mean, it's an irrelevant deformation, so its effects naively get weaker. But near the black hole singularity, the effects grow again. Yeah.
So there is, sorry.
One thing that I don't understand is why is this? So this is an effect that on the boundary is seen a very long time.
Yes.
Yes. So why is this different from, say, the hydrogen atom, where I do a tiny deformation? I will change a little bit the low-lying energy levels, a lot the ultraviolet, but if I wait a long time, even that little change in the energy level will change the dynamics. If you wait long enough.
I think it's more analogous to having a very heavy nuclei, where you have chaotic. So I think it's not very different from a physical setup where you have a very complicated nuclei, which has random matrix statistics, and you perturb the theory by changing, let's say, some of the, changing some values of the couplings in that theory. It's different from the hydrogen atom because it's important that the theory is chaotic in order to have the effect which I described. I think if you computed the Renyi 2 entropy of the hydrogen atom, where you perturb, you turn on some splitting effect, let's say, I don't think you would ever run into a unitary problem. What was important is that there's a very dense set of states that correspond to random matrix statistics, and they get mixed up somehow. Yeah. That was not an optimal answer to your question, but I'll stick with it for now. Okay, so yeah, you can also discuss some of the wormhole solutions more explicitly in gravity. I would just show you geometrically that there's a very beautiful quotient construction where you just take the disk solution and you do some cut and paste and you get a wormhole solution. So you can quite explicitly discuss the actual replica wormholes in the setup. And for example, this predicts something for G left right, the correlator between the left and the right side. And we see a very rough qualitative agreement with those predictions in our numerics. Yeah, okay, these are some details about the gravity solution. Okay, so yeah, I haven't discussed many things about this. One, for example, is just that we can do this whole analysis analytically using large QSYK. It also has some implications for the Schmidt Echo. So in the Schmidt Echo, what you do is you consider a theory with coupling J, right? You evolve with some Hamiltonian, Hj, and then you evolve with the inverse time evolution with Hj prime, right? And then you look at the overlap of the two states. So it's very similar to what we've been discussing. Essentially, the relationship is that in the Schmidt Echo, you're essentially considering the overlaps of two different states, which is like a matrix element of rho. Whereas in our case, we're actually considering these particular combinations of rho. But as a side product of our exploration, we were able to calculate the Lyapunov exponent associated with the Schmidt Echo. And we showed that in large QSYK, the Lyapunov exponent for the echo agrees with the usual Lyapunov exponent defined by the OTOC, the out-of-time correlator. So a priori, those don't have to be the same, but in this model, at least, they're exactly the same, even at finite temperature. Yeah, there's another way. Yeah, just as a side comment, you can kind of think of this as saying that the couplings are a cryptographic key to decoding the interior. So if you throw some information into a black hole, right, if you don't have the password of the black hole, which is the couplings that you used in making the theory, you won't be able to decode the information. Yeah, we specialize the low dimensions, but we speculate a bit about higher dimensional solutions, which we believe will have similar features as our discussion. So in particular, in n equals 4 super Yang mills, you can consider super Yang mills, let's say on the plane, right? And you have one value of the coupling constant G squared on one side and a different value G squared prime on the other side. And this corresponds to some sort of brain that you insert that goes into the bulk. More precisely, the dilaton has different boundary conditions, and across this junction, the dilaton has some profile. So that corresponds to, so if I were to draw a picture, right? Here's G squared here and G squared prime here, right? The bulk picture, which is this direction, has roughly something like some sort of brain that goes between the two sides, and that's basically the dilaton changing. On this side, the dilaton has a value corresponding to G squared prime. On this side, the dilaton has a different value, and across this junction, there's some interpolation. It's a smooth interpolation, so it's not exactly a brain, but it's roughly this form. And what we're essentially saying is, if you have a torus, there can be another side here, and we believe that but this picture, but there's a highly suggestive picture that suggests that we would be able to find wormhole solutions in using the Janus-like setup, but on a torus instead of on the plane. Yeah, another thing that I'll just quickly mention is it's very tempting to speculate about the black hole singularity, and what I'm about to say really quickly is just pure speculation at this point. But if you look at the effect of an irrelevant operator in the bulk in, let's say, JT gravity, right? So this is the Penrose diagram of a near extremal black hole, right? For a near extremal black hole, there's an inner horizon right here, and then there's some outer horizon. If you turn on some irrelevant perturbation in the dual boundary theory, and you look at the effect of the perturbation as you go this way, the effect is very minor. It doesn't do anything, basically, the irrelevant deformation. But if you continue to look at the effect as you approach the inner horizon, it gets very strong. So the effect of irrelevant operators in the dual geometry is basically kind of what you expect, which is that it does very little unless you're very close to the black hole singularity. So this suggests some potential connection between the effect of the black hole singularity with bulk reconstruction. What I just said was sort of purely speculative, but we find it suggestive at least. Okay, thanks very much.
To do your calculations in many points, you had really to compute an overlap between two different J's, right?
Yes.
For instance, the row ij, jk, etc.
That's right. That's right.
So that's not a classical effect, because in a classical effect you would have only the
It'd be
diagonal element.
That's right.
So how much of this will survive if you interpret instead the uncertainty in J as just classical ignorance? So you have just a probability distribution of J's and you are doing an ensemble average.
Yes, yes. Thanks for the question. So another setup that you can consider, what we considered was TFT J entangled with J, and then sum over J. Mm-hmm. Another thing you could consider is just rho J tensored with, well, okay, this is a little bit bad notation, but rho J, right? This is rho J of the quantum dot, of the dot, and this is rho J of the reference. They're not the same density matrix. But this would be a much more classical setup, right? And if you did this computation, then what you would find is that there are no wormhole effects that involve these off-diagonal things, and that, that would be much more analogous to the classical situation, right? But what you can say is, even in this setup, right, where you just sum over J, this is roughly like, you toss some coins, and based on the outcome of the coin toss, you choose the value of the coupling that you then evolve your theory with, right? But you can always say, well, this classical coin toss was actually a quantum variable if you include all the environment around it and so forth, right? You can purify that description, and then you're back to the original description field. So in other words, if you compute the entanglement wedge of the purified version of this, where you include all the environment, you're back to this setup. But that's just saying that in order, the entanglement wedge of the coin is trivial, but the entanglement wedge of the coin plus all the photons that have ever hit it and so forth, that contains the black hole interior. Another thing, let me just make another more technical comment. So this rho ij, as you said, semi-classically, you expect it to be very close to a diagonal matrix, right? And that's exactly what we see. So the prediction from semi-classical gravity is actually that it becomes essentially a diagonal matrix in I and J. But a diagonal matrix in I and J has an entropy which is proportional to the entropy of the Hilbert space of this system, right? And this system has an infinite dimensional Hilbert space, whereas this system was just a black hole and it has a finite dimensional entropy. So that's the unitarity paradox that we're discussing. Somehow the classical entropy that we get from doing the classical computation gets too big for these rho ij's, and you have to include these subtle quantum wormhole effects, which give you off-diagonal contributions to this density matrix and lower the entropy down to what is required by unitarity.
So you mentioned that the Lyapunov exponents for the Schmidt Echo and OC seem to agree in the case they studied.
Yes.
Is this some kind of generic feature for holographic theories?
Yes. I think the answer is yes, but I don't have a proof of it. I think it'd be really nice to have like a Malazan Stanford-Yang argument, which would say that the Lyapunov exponent of the Schmidt Echo is bounded by 2 pi, and that in holographic theories it's saturated 2 pi over beta. I don't know that exactly. I don't know how to make a statement like that. In the case that we considered, well, in the bulk case, in one of the bulk cases at least, it seemed quite plausible because essentially changing the boundary condition was like inserting an operator, right? In the case of a BFCFT. But for other deformations, it's not so obvious that there's a local effect of changing the boundary conditions, right? Changing the boundary conditions involves changing something along this entire contour. It just happens to be that in the BCFT case, you can summarize this effect by inserting some sort of boundary condition changing operator. That's right. And so in that case, I think we expect the answer to agree with the gravity answer, the maximal Lyapunov exponent. And then we explicitly calculated in large QSYK the large Schmidt Echo Lyapunov exponent, and we got that it was the same as. But that's an additional miracle because, the Lyapunov exponent in large QSYK is only maximal at low temperatures, but we found that it was in agreement at all temperatures. That calculation involves, well, it literally involves this contour, right? So you take the thermal field double with some value of J, evolve to some point, and then change the coupling and evolve backwards in time with a different contour. And in large QSYK, which is described by a Liouville theory in the G and sigma variables, that corresponds to just essentially putting some discontinuity in the large n variables, the G variable, and therefore you can solve it analytically using just the standard techniques of solving the Liouville equation.
Right, let's thank Henry again for his